Well, good morning, physics students. And my dog just walked in. Oh, come here. Come here, James. They want to see you. All right. Ginge, say hi. Say hi to the physics students. Okay, that's enough of you. You go away. Nope. Oh, my goodness. All right, guys. Today, we are going to talk about something called vectors. Okay? There are two types of numbers. Numbers that just have a value like 50 grams or 273 Kelvin. Those numbers are called scalars, scalars or ERS, scalars. Those are just numbers that, like I said, they have a value. I weigh 174 pounds. No, there's no question left after I say that, except why do you weigh so much? I could say it's 70 degrees outside. Okay, 70 degrees. You don't need to know any more. You know all you need to know. So scalars are the types of numbers we've been dealing with in chemistry. I've got 50 grams of calcium chloride. I've got a freezing point of negative 15 Celsius. But there are other types of numbers that we use, and they're called vectors. And vectors are perhaps the most important types of quantities that we'll study in physics. You may have talked about them a bit in Miss Teague's class. If not, put my kiss mug down there. Thanks, Cade, once again. If you haven't talked about them, let me just try to give you a brief idea about them, and then we're going to go into some calculations. Let's say you live in Dimick. You live in Dimick, and here's your town here. You have little houses, and, little building in Dimick, the one that's there. You have maybe a happy little tree. And so you're living in Dimick. And someone says to you, I want to go to Montrose. And you say, oh, no problem. And they say, how far is it? And you say, well, it's 8 miles. I don't know if that's correct or not, but you say it's 8 miles to Montrose. Okay, so you don't tell them any other information. And let's pretend there's no roads or anything. This is a hypothetical situation. We're just in Dimick here, and you say, okay, here we are in Dimick. I'll just call that D. And you say Montrose is 8 miles away. Well, that could mean Montrose is there 8 miles. Maybe Montrose is here. Maybe it's here. Here. As a matter of fact, if we have a circle of radius 8, it's not a very good looking circle, basically, if you're in Dimick and you want to go to Montrose and you say it's 8 miles away, you have to walk 8 miles and just keep traveling around that circle until you find Montrose. That's not a very efficient way to do things. So we have to give some direction to this 8 miles. So we say, okay, I'm in Dimick, and I know I have to go 8 miles northeast. 8 miles northeast. Well, that still doesn't quite give us enough information, because here's north and here's east. So if you imagine this as like a quadrant, you're saying, well, where am I going to go here? I have a whole 90-degree arc that I can traverse to try to find Montrose. So we have to be a little bit more specific. Let's say, let me use a different color, Montrose is right here. And I draw a line like that. Well, it's still going to be 8 miles, but we have to say, well, let's call this dm, this distance, dm. And I'm going to draw a line over it, sort of an arrow-looking thing. And that little arrow-looking thing represents a vector. Now, in textbooks, you're going to see vectors represented as bold-faced numbers, or I mean bold-faced letters to designate things. When you write it, you can't write in boldface, so you just go ahead and put a little arrow above it. So you have to specify it. You say, okay, this DM, Dimick to Montrose, you say 8 miles, and let's say that this angle here might be 30 degrees. 30 degrees. So that's how we would designate this quantity, this idea of getting from Dimick to Montrose. You say distance and direction. And this happens to be called polar coordinates. And polar coordinates mean that, we're talking about a circular coordinate system. And you probably learned that last year as well. If not, we're going to go through polar coordinates and how to convert back and forth between polar and Cartesian coordinates. So, as you can see, a vector is a little bit different than a scalar. It has magnitude and direction. The magnitude is 8 miles. That's how far we are from Montrose if we're in Dimick. Now, how to get there? We'd have to go 30 degrees north of east. So, if we want to just talk about the magnitude of a vector, we write that a little differently. It's kind of like writing the absolute value sign, except it's a double sign. What these little double these double lines mean is the magnitude of the vector. That's just 8 miles. So we have a magnitude and we have a direction. Please keep that in mind. That's what makes a vector a vector. If you continue your education through physics, let's say you end up majoring in physics or engineering, you'll get into other types of numbers called tensors, which are a vector is actually a subset of tensors, but they get a little bit more complicated. So we're not going to really mess with those in this course at all. That's if you're going to be taking sort of a graduate level physics course, you'll deal with those. Okay, so how do we deal with vectors? Polar coordinates are based upon a circle. And again, that's not a very good looking circle, but you're used to the unit circle. You've been dealing with that for a year already. And we know that the unit circle has a unit radius, a radius of 1, and then we have our different angles on this. So we can extend that to any size circle. So we can say in polar coordinates, we represent something by r and theta. Okay, so we have a function of radius and angle, and this would be polar coordinates. And we're going to have to learn how to deal with those and how to go back and forth between polar coordinates and Cartesian. And don't get worried about these names and these symbols. It's all very simple. It's all very straightforward. And once you go back and think about what you learned in trigonometry, you can go ahead and really easily go between polar and Cartesian coordinates and deal with vectors. So if I'm looking at vectors, let's go ahead and redraw our little Dimick to Montrose guy right here. Okay, and let's just call this vector, we'll just call it S, because I hate to keep writing dm. We'll just give it a name, S. S in physics usually stands for position or some sort of a distance, so we're going to call it that. So let's take a look at this in terms of Cartesian coordinates. I can have a coordinate system, x, y, it looks like that. And let's say we're here at the origin. This could be Dimick again. We can also say, well, hey, I can draw this same vector on a Cartesian plane. Okay, no big deal. No big deal. So you know that in a Cartesian coordinate system, we represent a point by an ordered pair. Let's call it x sub 1, y sub 1. You can call it whatever you want to. And this is our vector S. Okay, now how does this relate to that? Well, let's take a look at our magical right triangle. It doesn't look so right from this angle, but we know that we've got that side, the x side, and the y side, if you will. And here's our angle, theta, and this is our x value and our y value. And you know all the relationships. You know how to go from this to this and this to this without even knowing that you know it. Let's think about it. How do we get our angle here? Well, you know how to get the angle. The angle is going to be the arctan of y over x. Right? So, and we know how to get our s vector because we know that s squared is equal to x squared plus y squared, right? This dog. So we go ahead and use Pythagorean theorem. S is equal to the square root of x squared plus y squared. And we know all the relationships we need to know. We know that I can get the value of x, y, and s by using all of my relationships. This dog is driving me crazy. So I told you in an earlier video that x is going to be equal to, in this case, s, the magnitude. That's cosine theta. X is equal to s times the cosine of theta. Y is equal to s times the sine of theta. So these relationships help us to go back and forth between Cartesian and polar coordinates. Very easy stuff. It takes a little bit of practice if you don't remember it from last year, but we certainly can take some time and do that. So just, again, these relationships are going to come back to, I don't want to say haunt us, but come back to be useful tools for the entire school year. Okay, now let me look at some physics examples. Let's say, for example, we're looking at a force. Okay, this is Cartesian coordinates, x and y. And I want to make sure I don't forget anything. So I have a force F with an arrow above it like that. And what we're going to need to do is you're going to need to understand how to break that up into components. So let's say this force is 20 pounds. I'll use pounds right now because we're used to that. So if I'm pulling on an object, with a force of 20 pounds at some angle theta. Let's say theta is 45 degrees because everyone knows the sine and cosine of 45 degrees. So we will oftentimes have to break this up into its components. Its x component and its y component. The way we say this mathematically is the force vector is equal to the force vector in the x direction plus the force vector in the y direction. Now, it's not just as, this looks like a very easy relationship, but don't forget, we're adding components to get a resultant. And if we have more than one vector, I'm going to teach you how to apply this rather simple looking equation, but we have to do a few more things when we go ahead and do that. So in this case, if we want to get the x component of the vector, it's just going to be 20 times the cosine of 45. That's my x direction. That's the magnitude of my x vector, and we know its direction. It's right along the x-axis, so we'd be able to go ahead and solve for that. So what's that going to be? That's going to be 20 times root 2 over 2, and that's going to be equal to 10 root 2 pounds. I think that's right. You can go ahead and solve that for yourself. And then the y direction, in this case, since I chose 45 degrees, will be the same. It'll be 20 times the sine of 45 degrees, which is going to be, again, 10 root 2 pounds. And you have to have a unit, okay, because these are vectors. They have magnitude and direction, and the magnitude would be this value right here, and the direction would be along the x and y axis. There's another way we can write that. We could write it like this in what's called unit vector notation. Okay, now unit vector notation is kind of cool because we pretend, well, we don't pretend, we imagine, I guess you could say, a hypothetical little vector. I need more than 2 colors of pens for this kind of stuff. A unit long one in the x direction, and one in the y direction. Okay? And these are little vectors, and we can multiply vectors by a scalar to make them any length we want to make them. So we have names for these unit vectors. We call them I hat and j hat. Okay, that little cap on there means we call it hat, but all it is doing is representing a vector. So this is the x unit vector in the x direction, and this is the y unit vector. And if we extended this to 3 dimensions, we would have k hat. That would be in the z direction, but we are pretty much only doing 2-dimensional motion in this class. We're not worried about 3-dimensional motion. So what we would say is, okay, my force vector from my last problem could be written as 10 root 2 I hat plus 10 root 2 j hat pounds. Another way to represent the vector, okay, is stressing the fact that we have 2 components, an x component and a y component. Now, these are not always going to be the same number. For 45 degrees, I just put that there because it's easy. Let's take a look at a real example problem here. Okay, so I have an example. I'm going to write it down. It says a plane, an airplane, takes off at an angle of 15 degrees to the horizontal with a velocity of 150 meters per second. Calculate its horizontal and vertical velocities. Ooh. Okay, well, a little sloppy there, sorry about that. First thing I always do, and in physics, I encourage you to always sketch the problem. Sketch and be organized. Now, my handwriting's a little sloppy, but I can still be organized with this. Plus, I'm trying to go fast. I don't want to make a 35-minute video. So, in the simplest form, we can draw a coordinate system, and we can draw, well, we know that we have an angle of 15 degrees and 150 meters per second. So my vector, let's call it v, is equal to, well, we have 150 meters per second and 15 degrees. So let's sketch that. I'm trying to draw 15 degrees. I don't know how close I am. X and Y. So now we know this is our velocity vector v. So we are asked to calculate the horizontal and the vertical velocities. We call these components, by the way. And when we add components in a vector fashion, we get the resultant. So those are 2 words you want to look up and have in your notes. Components and resultant. All right, so my angle is 15 degrees. So let's go ahead here and figure this out. Well, my x direction, my x velocity, oh, I wrote force, that's not force, it should be velocity in the x direction, is equal to cos 15 degrees times 150 meters per second. The units will be meters per second, and the velocity in the y direction will be sine 15 degrees times 150 meters per second. So let me see here. I have my calculator. Cos of 15 times 150. Okay, so this is 144.9 meters per second in the x direction. And that makes sense because if you take a look, we're only 15 degrees above horizontal. So the bulk of that vector is going to lie along the x direction, that component. And then let's do the sine of 15 times 150. and I get 38.8 meters per second. So breaking this up into components, a velocity vector going 150 meters per second, 15 degrees above the horizontal, is equivalent to two vectors when you add them, one along the x-axis, one along the y-axis with these respective values. So we can go ahead and write that in unit vector notation, and we would say, okay, v, the velocity vector. Remember, this is just notation. We're going to work on breaking this down and spending a lot of time on this. But if you can get this much down, you're going to be in good shape. So it's going to be 144.9 I hat plus 38.8 J hat meters per second. And this is the unit vector notation. Again, this is just, don't be frightened by this. This is just saying, hey, these are the two components. We use I and J instead of X and Y. Don't ask me why we do that. It's just convention. So for today, I think that's about it. Yeah, that's about it for now. We'll be back with some more vector fun tomorrow. Take care.